Welcome to qnawire.
Hello everyone. In this problem, we are given the wave function to be the superposition of the first and third excited states of the wave functions in an infinite square well of length L. So we're told that the wave function looks like the following. So we have 1 over root 2 times the spatial distribution of the ground state wave function, so psi1x, times its corresponding time evolution function, which is e to the minus I e1 times t over h bar, plus 1 over 2 times the same thing for psi3, the third or the second excited state. Sorry, third excited state. Right? And then we're asked to find the probability distribution. The probability distribution is just the mod squared of this wave function, of this entire wave function, right? So it's psi star psi. And so all we have to do is basically multiply this function by its complex conjugate. And if you do that, then you should get something like a half psi1x squared, mod squared, plus a half psi3 mod x mod squared, plus 1 over 2, so half psi1 star psi3 times e to the it over h bar times e1 minus e3, plus a half times psi1 times psi3 star e to the minus it over h bar times e1 minus e3. Now, the thing to notice here is that two of these parts, so two things in here are real, right? So the psi1x mod squared is real, and the psi3x mod squared is real. And the other parts, so this function and this function, are complex conjugates of each other. So if you call this z, and you call this z star, then you have z plus z star. Right? What is that equal to? Well, if you have something like a complex number like x plus iy, for example, and then you add to that its complex conjugate, then you're going to add plus x minus iy. So you're going to get 2 times x. So you're going to get 2 times the real part of your complex number. So 2 times the real part of z is equal to 2x, right? So basically, what you're going to end up with then is that the probability distribution function is going to be equal to a half times psi 1 mod squared plus psi 3 mod squared plus 2 times the real part of this complex number that we got here. Now, we're going to rely on the usual form of these wave functions, psi1x and psi3x. So psi1x is equal to the square root of 2 over L sine pi x over L, and this is equal to the complex conjugate of this spatial wave function because it's a real function. Then psi3x is equal to the square root of 2 over L times sine of 3 pi x over L, and this is of course equal to its own complex conjugate as well. So we can use this to find, you can use these expressions to find what the values are at L over 2, which is the position where we're interested in finding the probability distribution function. So if we put in L over 2 is equal to x, we find that psi1 is equal to root 2 over L, and psi3 is equal to minus root 2 over L. So putting that back into our mod squared expression for the probability distribution function, we get that psi L over 2 mod squared is equal to a half times 2 over L plus 2 over L, right, because those are squared. So the squaring gets rid of the minus sign and the minus root 2 over L, plus 2 times the real part of a half times minus 2 over L. So this minus 2 over L is equal to root 2 over L multiplied by minus root 2 over L, coming from multiplying by psi1 star with psi3 and L over 2. And so we're going to get that we're taking the real part of this. So the real part of this is just going to be the part that goes with the cosine coming from the exponential. So we're going to get overall that psi mod squared at L over 2 is equal to 2 over L plus 2 over L minus 2 over L times the cosine of E1 minus E2 over H bar times T. Now, if I make the simplification that I call this combination of variables omega, then this can be simplified to 2 over L times 1 minus cosine omega t. And cosine omega t, I can say that is basically a double angle formula for 2 times omega over 2 times t, right? And then I can say that cosine of 2 times omega over 2 times t is cosine squared times omega over 2 times t minus sine squared times omega over 2 times t. The utility of doing that is that I can also write 1 as a function of this angle, right? So I can write 1 as cosine squared omega over 2 times t plus sine squared times omega over 2 times t. And so making these substitutions, we find that the result is equal to, so psi at L over 2 mod squared is equal to 4 over L times sine squared of omega over 2 times t. So this is the answer to the first part of the problem, which is just asking you to find the probability distribution at L over 2 as a function of time. And the second part is asking you to evaluate find what the frequency, what the angular frequency of this oscillating function is. And so if we call this part over here the actual frequency, omega prime is equal to omega over 2, depending on what I call omega, right? And so here we're going to have that this is E3 minus E1 over 2h bar, right? Because omega was E3 minus E1 or E1 minus E3. The point is that you're going to take the absolute value of that. And it doesn't really matter here because you're taking a cosine oscillating function, which is even, so it doesn't matter what the argument is, whether it's positive or negative. So I took this to be E1 minus E3, but you could have just used E3 minus E1, and that is generally what we would use. So we're going to take that to be omega, and we multiply that by a half. And so this is what we end up with. And then we're going to use the fact that En for this system is given by n squared pi squared h bar squared over 2ml squared. Right, so this is the general formula for the energy levels. Oops. Something bad happened over there. So this is the general formula. And then we're just going to put in the values for n equals 3 and n equals 2 and just power through the calculation. And we're going to find that it simplifies to omega prime being equal to 2 times pi squared h bar over m times L squared. So this is going to be the actual frequency or actual angular frequency with which the probability distribution function oscillates.